Okay, so once this opens, we are going to carry on with chemistry today. So we're going to look at shapes of molecules and then into how bonding and polarity and intermolecular forces create these different shapes of molecules. So what we're going to look at first is actually the actual shape that a molecule makes. So what their arrangement is, because we're quite used to regularly seeing images such as this. Let me get a picture up actually. Let's annotate this. Drawing. So you can regularly see a picture that would look like this, and I don't know why this isn't working today. And what would happen is I'm not quite sure what's happening. Here we go. So you can get a molecule, and sometimes the molecules, for example, H2O, will be arranged like this. You might have a molecule such as CH4, which would be shaped like this. You might get some other molecules like, let's see, double bond O, and they're in a linear plane. So what we're going to look at is actually how we maybe get these different curves forming and how we get all the different bond angles forming. That's the first thing we're going to look at. So they all make these different shapes, but what causes this one to be linear as opposed to this one to be what we call that Mickey Mouse termed shape, and what causes this one to be in that shape. So that's what we're going to look at first. So the thing that causes this is something called a valence shell electron pair repulsion. So what this is a theory, and it all goes back to that idea of charged clouds right back at the beginning, when we were sort of talking about all our electrons are arranged around in our atom around the nucleus in orbitals, and each orbital is in a different energy level. And so officially an orbital is a region of space where we're likely to find an electron. So we can draw them quite nice and neatly, like the image on the left, where we've got circles with electrons on them, and they're all sort of floating around and they're moving around and orbiting in a certain way. Realistically, so that's our Bohr model, what actually we have is we have something called an electron cloud. And so the electron cloud is basically all the probability density of the electrons, so the probability of where it is going to be. So our orbitals are where 95% of the time where we're going to find them. So to draw them nicely, we just say, oh yeah, the electron would be, for example, here and here. But actually, those two electrons on that first energy shell could be anywhere on that orbital at any time. So that's where we get that electron cloud.
Hello.
Hello. I don't know what happened. I think the internet just went.
It got stuck. It got stuck. I have been waiting for a long time. Just got stuck. Now it has come back.
Yeah. Okay. I just need to reshare the screen. Here we go. Hopefully it'll open again. So yeah, so rather than it being like a set defined place, we then say the electrons are there in this charged cloud. And so that's sort of what we're saying with a charged cloud is we sort of basically is actually, if we took an image of an atom again and again and again in milliseconds, the electrons would actually be moving. They're not in these stationary positions. So a charged cloud is actually where the electrons are placed. So charged clouds are quite an important part of this valence shell electron pair repulsion theory. So we're going to look into the repulsion part of this now. So repulsions, as we've talked about before, repulsions occur because the electrons have a negative charge. So because electrons have a negative charge, they're able to repel each other. Same concept as when we're talking about a magnet, negative charges repel. And actually this repulsions, and due to the negative charges of the electrons, are actually what determines the geometry of the molecules. So actually how the electrons are going to repel each other determines the shape of our molecule, the shape our molecule is going to create. Now, we can have different types of pairs of electrons. We can have lone pairs, or we can have bonding pairs of electrons. Now, lone pairs are held closer to the nucleus of an atom. So because they are held closer to the nucleus of the atom, they actually repel more as they are physically closer to each other. So we actually have this hierarchy from the most repelling to the least. So if we had a lone pair electron and then another lone pair, they repel the most. They repel the most because they're more physically closer. It's a lone pair and a bonding pair, so they're the medium repulsion, and then bond pair with bond pair has the least amount of repulsion. So this is the valence shell electron pair repulsion theory. So it's the fact that they're in the pairs and they're going to repel each other. But lone pairs are more repulsive than bonding pairs. So basically what happens is our electron pairs and we get our geometry forming. So we can have a molecule that makes a linear shape. And so what we have to really know here is if you can get shown an image of different molecules and get asked to say what type of what's the geometry of the molecule, or you could get told this is a linear molecule, can you draw it, or you can just get asked to draw it and say it's a linear. So for example here, our central atom on a linear molecule is always going to have 2 electron pairs. So it's going to have 2 electron pairs. So it's sharing here and it's sharing here. And the bond angle here is 180 degrees between the electron pairs. So it's 180 degrees. And another example of a linear molecule, I'm just going to draw another one on for you, would be CO2. C, double bond O, double bond O. And again, we've got that 180 degree bond angle there. So that's a linear molecule. A linear molecule, and our central atom has 2 electron pairs. So then we go on to, from a linear molecule, we can then go on to a trigonal planar. Now, actually, if we stay with linear for now, this is where we would often assume water would be like this and have the bond angle of 180. Now water doesn't. Water has, so that isn't water. Water has this geometry, and we're going to look at that in a bit later. That is because water is a polar molecule. So we're going to have a look at that later and discuss why water is a polar molecule and why water isn't linear. But carbon dioxide, for example, would be a linear molecule. So the next geometry layout for a molecule can be a trigonal planar molecule. So if a molecule is in trigonal planar, our central atom again has 3 electron pairs. So like when it was linear, it had 2 electron pairs. Our central atom this time has 3 electron pairs. It has a bond angle of 120 degrees. So this angle is 120, this angle is 120, this angle is 120. And that's all you really need to know. So if you ever see anything in this shape, it is a trigonal planar, and I don't know, 120 degrees, a trigonal planar molecule. Another example, here's another one I'm going to draw for you here. And our bond angle is 120. Then you can probably start to see that there's a pattern coming on. This time we will have tetrahedral. Tetrahedrals are when our central atom has 4 electron pairs. So you can sort of see the pattern that's starting to form. So our central atom here has 4 electron pairs. Now this time we have a bond angle of 109.5. So I'm just going to draw that on here. So we've got a bond angle of 109.5 degrees. And we've got those 4 electron pairs. Now, when we're hand drawing these, I'm just going to draw this one on by hand to show you. We draw them a little bit differently because it can actually be quite hard to show this 3D shape that we've got quite nicely shown here. Show actually that we've got one more towards the front, one more towards the back. So actually how we would regularly draw them is like this. So we do our hydrogen, go straight down to our carbon like normal. We'll have one hydrogen coming off the side like normal, and then we want to draw one as if it's behind and then one in front. So the one in front would look like this, and it's often shaded in. And then the one behind goes like this, and that's it, and that will give it that shape. So that is our tetrahedral shape. That's 109.5 degrees. Its bond angle is 109.5 degrees, and this is when the central atom has 4 electron pairs. And then we've got 2 more, and the next one from this is trigonal bipyramidal. Probably notice now with the patterns that's happening, this is when our central atom has 5 electron pairs. So our central atom has 5 electron pairs. This is what happens. We can get a bipyramidal shape also forming if we have a lone electron pair involved, but actually right now we're just going to worry about this one. But both of them have formed a trigonal bipyramidal shape. Now, trigonal bipyramidals actually have 2 different bond angles. We actually have 120 degrees from the equator, and then we also have 90 degrees from the equator to the apex. So this one's a little bit more complicated. So we've got those 5 pairs, but as you can see here, we've got our 90 degrees here, then we will have here our 120 degrees. And that is our trigonal bipyramidal. And then our final one that we need to know is this, is our octahedral. So our octahedral, our central atom has 6 electron pairs. So I'm just going to write 6EP there for 6 electron pairs. Its bond angle, as you can see, is 90 degrees. I'm just going to draw you another example to show you, like I did before, how you would draw it yourself to sort of. So these images are really nice for the sulfur hexafluoride to actually show you the molecular geometry of it, the bond angles and the electron pair geometry. Actually, what I want to show you now is how we would draw this ourselves if you were asked to draw this in an exam, but with another one. So if we're doing, I'm going to do sulfur hexachloride. We'll have a sulfur, we'll have a chlorine, sulfur, a chlorine, same as normal. These ones show that it's going behind. These ones show that it's going behind. This one shows that it's coming out in front. This one shows that it's coming out in front. Colour them in and colour that in. And so you can see that you've sort of got that central area, like we've got here. It's that central region, and then we've got the top and bottom. And so that's our molecular geometry, which is really important actually that we know. So what's really important for these is that we know the names of them, how many electron pairs are attached to the central atom, the bond angles, and actually the names and how to draw them. So that's really, really important. Now we're going to look at polarity in a bit more detail, because obviously I mentioned I mentioned water earlier, and water would go, okay, well, we've got oxygen, 2 hydrogens, that should be a linear molecule, and it's not. So actually, we're going to look into polarity in a little bit more detail and just have a discussion about why some molecules aren't and don't work that way. So obviously here we've got a molecule of water, and it's clear that that isn't a linear pattern. It doesn't have that 180 degrees for its bond angles. And so this all goes back to the idea of electronegativity. So what happens is when we have a bond between 2 unlike atoms, one will have a stronger attraction to the electron pair than the other. So basically, if both the atoms were hydrogen, they would have exactly the same attraction because they're the same atom, they have the same electronegativity. When we have 2 unlike atoms, they have different charges slightly. And so one has a stronger attraction to the electron pair than the other. So what happens is when this happens is our electron pair doesn't end up being at the center. So rather than getting this, so our electron pairs at the center, so we get that nice 180 degree. Here we get our electron pair being pushed slightly off center. And what this does is this causes a buildup of positive charge on one of the atoms. So, for example, in water, we have a buildup of positive charge in our hydrogens, and we have a buildup of negative charge in our oxygen. So the electrons spend more of the time towards the oxygen atom than the hydrogen atom. So this is the ability to attract the electron pair, and this creates the electronegativity. So the ability of one of the atoms to attract the electron pair stronger than the other creates this electronegativity. So that's what happens with water. Now, electronegativity, we actually use a specific scale to measure electronegativity on. And the scale that we measure electronegativity on is called the Pauling scale. And so this is our electronegativity scale. So Pauling, it's our scale for electronegativity. It was named after the person who discovered it. And our most electronegative atom is fluorine. And fluorine has a value on the Pauling scale of 4. 3 other highly electronegative atoms are oxygen, chlorine, and nitrogen. Oxygen has an electronegativity of 3.4, chlorine 3.2, and nitrogen with 3.0. 2 examples that actually have quite a low electronegativity but similar are, for example, carbon and hydrogen. So carbon has an electronegativity of 2.5 and hydrogen of 2.2. So what happens is if you have a molecule that's made up of 2 unlike atoms, 2 or more unlike atoms, and they've got a charge difference. So for example, we could have chlorine and fluorine building up together. So let's say we had a chlorine and a fluorine, not chlorine, carbon and fluorine, for example. There would be a charge difference because our carbon's got a charge of 2.5, our fluorine's got a charge of 4. So our charge difference, a charge difference is called a dipole. So you'll have heard of dipoles before. So the charge difference is called a dipole. So HCl, for example, so HCl, we've got charge of 2.2 on hydrogen, 3.2 chlorine. The charge difference here is a charge of 1. So actually that would create a dipole. So we would say this is a polar bond. And a polar bond is when we have a large charge difference. Whereas, for example, carbon and hydrogen, if they bond together, we've got a charge difference of 2.5 and we've got a charge of 2.2, small difference of 0.3 3. So we would say this is a non-polar molecule. So this is a non-polar bond, sorry, a non-polar bond. And this is all to do with that charge difference. If it's a large charge difference, it forms a dipole, and the larger the dipole, the more likely it is for the bond to be polar. So polar molecules, I'm just going to have a little chat about what polar molecules are and why they occur. So an example of polar molecule, we've got one here, and we've got CHCl3. So just so you know, this is a carbon atom in the middle, got hydrogen and 3 chlorines. It's a polar molecule, and we're going to talk about why it's a polar molecule if we go and have a quick look back at our Pauling scale. So actually, on our Pauling scale, the charge for hydrogen would be 2.2. Our charge for our carbon is 2.5. So actually, this is a non-polar bond here between the carbon and the hydrogen. So if it was just the carbon and hydrogen, that'd be fine. But we also have these chlorines involved, which obviously have a charge of 3.2 each. So their charges are a lot higher. So this is showing our dipole movement. So what ends up happening is we end up with this polar movement because we don't have, because they've got these polar bonds all involved with each other. Now they don't cancel each other out in this situation. So whilst these two might cancel out, we've actually got a net change over here. We've got a difference each time of 0.7, so it's a lot larger, so it's going to have a pull towards the chlorine. The hydrogen, the carbon's going to have a pull from the hydrogen, but then the chlorines are going to have a pull from the carbon. However, a molecule with polar bonds isn't always a polar molecule. This is a polar molecule. It's got polar bonds and is a polar molecule. But what can happen is our bonds can cancel out. And I don't know if I've got an image of this. Let's have a look. No. So they can cancel out with each other. And so an example of one where they could cancel out and you end up with symmetrical bonds would be this one. We've got CCl4. Now, we get a symmetrical formation because actually we've got 2.5 in the middle, but all of these are 3.2. So we've got an equal pull here. So whilst you've got polar bonds forming between the carbon and the chlorine, the charges actually cancel each other out. And so what ends up happening is we get a symmetrical bonds forming a symmetrical, so it causes us to have a non-polar molecule. So whilst it has polar bonds, the molecule is actually non-polar because our bonds have cancelled out. And that's really important to remember, that just because there is polar bonds doesn't mean that the molecule is polar. Water, for example, is a polar molecule because the bonds don't cancel each other out in that situation. Just going to actually have a talk through a way that we can actually remember if a molecule is polar or not. So a molecule is polar if there is a charge separation between each side of a molecule. And there's a good way that we can work this through. So we can say, okay, we've got polar bonds. So you can look at the molecule and we can decide, has it got polar bonds? If the answer is no, we know that it is a non-polar molecule because polar bonds have to be there to begin with. If the answer is yes, we need to ask this question. Do they cancel out? If the answer to that is no, then you have got a polar molecule. If the answer is yes, then you have a non-polar molecule. So that is a good stepwise process that you want to work through every time to try and decide if your molecule is going to be polar or not. And so this is a great way to remember it. So a molecule is polar if there is a charge separation, so a charge difference, a charge separation between each side of a molecule. So that's really important. That's a really good definition to remember and actually to understand. So it's between each side of our molecule. So if one side is slightly more polar than the other, then we will get this polarity forming. And so that's really, really important actually. And so if a molecule is polar, that actually does change its geometry. And it doesn't always, but it can change the geometry of the molecule. So what we're going to have a look at now is the 3 different intermolecular forces, and then we're going to have a look at some exam questions. So move this on. The first intermolecular force that you will come across is, and this is our weakest as well, it comes under 2 names. Well, there's technically 3 names it comes under. It can either be called an induced dipole-dipole interaction, or van der Waals forces, or occasionally it can also be referred to, you might see it in books sometimes, referred to as, I'm just going to write it over here, actually, London forces. So it has 3 possible different names. So depending on what textbook you're reading, you could come across either one of these 3 different names. It's just really important to remember that van der Waals are the same as induced dipole interactions, and they're the same as London forces. We do have another type of intermolecular force with very similar name to dipole-dipole interactions. So what's really important to remember is these ones are induced. So we're going to talk about what induced ones mean, but these are different. Really important to remember, these are our weakest. These are our weakest intermolecular forces. And so like we just spoke about with polarity, a dipole is just a charge difference. It's where we've got a difference in charge between one atom and another atom. So here we talk about intermolecular forces. So these are our forces inside a molecule. So these are our weakest, and they're formed of temporary dipoles. So what we have to remember, and it is sometimes quite hard to remember, is whilst we have these flat, still images of an atom and an atom, but actually those electrons are moving all the time. And van der Waals forces basically work on the concept that we are temporarily some atoms, the atoms can become polarized. So one atom will have a more positive charge, one will have a slightly more negative charge, but that changes constantly. It's not a set in stone. So this is what we mean by induced dipole-dipole. So these are temporary dipoles. They are not constant and they don't last. And this goes back to that electron cloud idea. So it's that idea that all of our electrons are moving around our nucleus. So our electron cloud is constantly in motion. And so that's something really, really important that we remember. I'm just going to pop it on here, is that our electron cloud is constantly in motion. Otherwise, it can be quite hard to sort of picture the difference between induced dipole-dipole, which this is, van der Waals. I'm going to call this our number 1 forces. And our next one, which is a permanent dipole-dipole. It can be quite hard to tell the difference if we forget that our electron cloud is constantly in motion. So our electron clouds are constantly in motion. So because of this, we're basically thinking about the density of the electrons. Where are most of our electrons located at one point? So what we often draw is sort of where this step one is. We would draw on an image. Okay, here's my first atom. It's got 4 electrons. They're here, here, and here. Here's my second atom. It's got 4 electrons. They're here, here, and here. But when we think about the electron cloud theory, then our electrons are constantly in motion. What can actually happen is our density of our electrons can all be on one side, and then they can move to somewhere else, and then they can be somewhere else again. So, for example, this atom 1, in the next second, we could actually end up with it looking like this. A minute later, we could end up, or even a second later, looking like that. And then it could look like this. There's one over there. So it's just changing constantly all the time. So that's what's really, really important to remember. Okay, so we've got an electron cloud. It's constantly in motion. What happens is we get this idea that basically, if over here, if in our atom 1 over time, all of our electrons suddenly go and move over to this side of the atom, we know electrons repel. But also, because electrons have a negative charge, your nucleus has a positive charge, the electrons will attract the nucleus. So what can happen is our atoms become polarized and become attracted to one another because we have a slightly negative charge over here, and we've got our slightly positive charge over here, and then they attract each other. Now, we say these are partial charges. We do not say they are permanent charges. These are partial charges. It's partially negative, it's partially positive, and then in the next second, it could be neutral again. So we have partial charges forming. These change rapidly, and that's really important to remember. Is that they change rapidly, so they don't stay the same all the time. So the partial charges of one molecule, and they can push away electrons in another or attract them. So for example, on this one, we've got them all over here, so it would actually push those electrons away over there and attract the nucleus towards it. And the temporary dipoles induce dipoles in nearby molecules. So temporary dipoles induce other temporary dipoles in nearby atoms. So this one, atom 1, has induced a temporary dipole in atom 2. Now they can have varying different strengths, and that's all to do with the amount of electrons. So the strength of a van der Waals force, or an induced dipole-dipole interaction, relies on the number of electrons in the molecule. So basically, strength equals the number of electrons in the molecule. The more electrons that are present in the molecule, the stronger the van der Waals forces. The least amount of electrons in the molecule, the less strong the van der Waals forces are. So that's basically what van der Waals forces are, and it's these induced dipole-dipole interactions. So it's this idea that the electrons are moving constantly. Suddenly they could all be on one side of the atom, as for example over here. So we have a partially negatively charged atom over here. It's a partial dipole. It's induced, and actually it's going to induce a dipole over here. So it pushes those electrons away. It pulls this nucleus towards it, and they have an induced dipole reaction here. And so then this bit here, this is actually our van der Waals force there. That's our van der Waals. That's reacting. That is the force together from this induced dipole interaction. So that is what an induced dipole interaction is. Now we're going to have a little look at what a permanent dipole is. So we have 3 types of intermolecular forces, and this is our second one. So it comes in the middle for its strength. So permanent dipole-dipole interactions come in the middle. These are our middling for strength. They're stronger than our van der Waals forces, but our next intermolecular force, which is hydrogen bonds, is weaker than that. So what we have here is we actually get a permanent dipole. being formed. And so one side is has a negative charge. So for example here, so this here is our permanent dipole-dipole interaction. So this part is actually our permanent dipole-dipole interaction. So we're not talking about our bonds between our hydrogen and our chlorine. And in the molecule, we're talking about here between the molecules. So we've got this so we have this negative charge, which is on one side, and we have our positive charge on the other. As we know, positives attract negatives of another molecule. So our positive charge of a hydrogen over here attracts the negative charge of a chlorine of the other molecule over here. And what happens is in permanent dipole-dipole interactions, they actually line up in a linear pattern. So they always line up, and it's just because of their interaction. So they line up, and this is actually occurs in a liquid or in a solid. In this fashion. So in this fashion, you can see on here, they line up in this way, and they always line up if a permanent dipole-dipole interaction is found. Now, they are only found between polar molecules, which makes sense. And because we're not inducing a dipole, this is something that is there. So it's really important to remember these are only found between polar molecules. So we're not inducing polarity, and this is found between polar molecules. And that is because they need a permanent dipole. So that is why they're harder to break, because it's a permanent dipole. It makes it harder to break because that bond is always going to be there. It's not going to be moving at any point. So we need that permanent dipole to be present to get that dipole-dipole interaction. And so they line up in this fashion. So van der Waals can actually form between any molecules, any atoms. Van der Waals forces can happen because it's that whole idea in the theory that the electron cloud is moving constantly. Therefore, at some point, a dipole is going to be induced between the two different atoms. Permanent dipole-dipole interactions can only happen between polar molecules, and that leads us then on to our third and strongest intermolecular force, which is hydrogen bonding. Now, hydrogen bonding can only occur between certain atoms. Now, hydrogen bonds are our strongest intermolecular force. Now, we don't go into bonding. It's a bit of a confusing one because we call it a bond, and it is, but it's actually an intermolecular force. Things like covalent bonding and ionic bonding are different. There are actual official bonding, and hydrogen bonding is actually an intermolecular force, but this is our strongest of the three intermolecular forces. So that's always good to remember, because you can get asked about two different molecules, why it takes more energy to break one down as opposed to another. And this is what you're going to need to look into. You need to investigate, okay, van der Waals forces are going to be present in all molecules, but does this molecule that I'm given, does it have a permanent dipole interactions? Does it have any hydrogen bonding? So hydrogen bonding, it is the strongest. It is a strong permanent dipole force again. So it's almost like the level up from the one that we've just spoken about. So this is a strong permanent dipole force. So it's basically the next level up from a permanent dipole interaction. But it is only found when you have hydrogen bonded to either, I'm just going to pop this here, found when hydrogen is bonded to either, and it's these possible atoms: oxygen, nitrogen, or fluorine. So hydrogen bonds can only happen between hydrogen and oxygen, nitrogen and fluorine. Cannot happen between any others. So for example, some molecules that will have hydrogen bonding in them would be water, hydrogen, oxygen, obviously, hydrogen fluoride, which would obviously be your hydrogen and your fluorine. And then an example of hydrogen and nitrogen would be ammonia, where you've got some hydrogen bonding involved as well. Hydrogen, what happens is if we think back to the Pauling scale, things like oxygen, nitrogen and fluorine, well, fluorine is our most electronegative atom. Nitrogen is then quite high up there along with oxygen. So, sorry, I just need to sneeze. So hydrogen in hydrogen bonds is bonded to extremely electronegative element. So these are all extremely electronegative. And so what happens is the hydrogen develops a strong positive dipole, which we've got here. And the hydrogen is so small, it has a high charge density, which means that because it is really small, the charge density ends up being very, very, very high, which causes these very, very strong hydrogen bonds to form. What we're going to do for the last 10-15 minutes is now have a look at some example questions that you can get asked about these. So here is an example of a question that you can get asked. So you can be told, this is all to do with bonding and molecule geometry. So carboanions are anions where the central carbon has 3 bonds and a negative charge. An example of carboanion is CCl3-. And what you're asked to do is compare the molecular geometries of CCl3- and CCl4. So you must include how many bonding and lone pairs are in each molecule and the bond angles around the carbon in each case. So actually what the first thing is you would do is you would actually draw this out. It's quite important to be able to draw these out. So carbon and Cl4, well actually you would have your carbon, you have chlorine, chlorine, and obviously that's one that we talked about earlier. We cancel each other out, so this would be a non-polar molecule. And then we're going to have carbon and Cl3, but we've got a lone pair, so we're going to have a lone pair drawn on here, and that will cause this to happen. So we're going to talk now about how many bonding and lone pairs we have in each one. So it would have been helpful if I'd drawn it on this page, but they might actually move across. That's not helpful where I've got them. So what we're going to do is first thing we do is we say that any electron pairs repel each other in molecules. And so electrons that are in a lone pair will repel other electrons more than the bonding electrons. So that's really important, what we learned about at the beginning. So therefore, our CCl3- will have a trigonal pyramidal shape. And that happens because we have our lone pair here, and our lone pair will repel other electrons more than our bonding electrons. So we would end up with this. We've got a chlorine, and we will get a trigonal pyramidal shape. Now, trigonal pyramidal shape, when we were talking about it before, it is very similar to a trigonal bipyramidal shape, but obviously it's only pyramidal because we haven't got, because we've got the lone pair at the top. So what we would have is this, Cl, Cl, and Cl. So that's our trigonal pyramidal shape. And as you can remember from a trigonal pyramidal shape, our bond angles are 107 degrees. So our bond angles here are 107 degrees, whereas our CCl4 would be a tetrahedral shape. So a reminder of tetrahedral, we've got our carbon, we've got a chlorine, we have got a very similar drawing to the other one actually. Chlorine, and then call that one in, our chlorine. Okay, so that is our tetrahedral shape. Our tetrahedrals have a bond angle of 109.5 degrees. So that is 109.5 degrees. So any electron pairs repel each other in molecules, which is how we get our bond angles. So that is our first important thing to say. Electrons that are in a lone pair, well, we've got a lone pair over here, will repel the other electrons more than bonding electrons. So these are all bonding electrons. So because of that, CCl3 will have a trigonal pyramidal shape, and the bond angles in CCl3 minus will be 107 degrees, whereas the shape of the CCl4 will be tetrahedral, and the bond angles in CCl4 will be 109.5 degrees. Okay, here's another similar sort of question. What is the shape of ammonia, and why does it form this shape? So you can get asked this to draw ammonia, and what actually is a very sensible place to start with a question like this would actually be to go out and draw the dot and cross diagram of an ammonia molecule. So that's what we're going to quickly do now. So whenever you're asked any of these questions, what you want to do is you want to draw out what it does, so what shape it forms. So what is the shape of ammonia and why does it form a shape? Well, actually, the first thing you want to do is draw out the dot and cross diagrams. So you want to draw it simply to show how many electrons are involved in the bonding. So as we should know from GCSE, this is what an ammonia molecule would look like. It's NH3. So we've got our nitrogen, got our hydrogen, hydrogen, hydrogen. Draw that there, draw that there, draw it there. I'm just going to get a different colour pen. Okay, so on nitrogen, we've got electrons for our nitrogen being drawn on now. And then I'm going to draw our hydrogen electrons on now. Okay, so that's our NH3, that's our ammonia drawn out as a dot and cross diagram. I'm probably going to draw that again over here, because I think I've actually got the rest of it on the next page. So let's draw that out again, just really quickly. So we've got NH3, so N, H, H, H. So we've got a lone pair of electrons up here at the top. Actually, I'm just going to change the colour of that so you can see that. So we've got a lone pair of electrons up here, and we've got 3 bonded pairs. So you want to state the number of bonding and lone pairs. As we can see from this image, ammonia has 3 bonding pairs of electrons and 1 lone pair. Our lone pair is up here at the top. Now remember, lone pairs have a larger repulsion than bonding pairs. So we're going to state what electron pairs do. Well, electron pairs repel each other. Electron pairs try to get to a position of maximum separation or minimum repulsion. This is a different way of saying the same thing. So when pairs are far away, they repel each other less. That's basically the same idea of it. So we're going to say what the difference then the lone pairs make. Well, lone pairs repel more strongly than bonded pairs, and this causes the bond angles between bonding pairs to decrease. And that's a really, really important part to remember, actually, is this part, is that lone pairs repel more strongly. So remember, we said lone pair repelling strongest, lone pair, bonding pair, middle, bonding pair, repel the least. So lone pairs repel the most than bonded pairs. So this causes the bond angle between bonding pairs to decrease. And that is because it's going to basically push them out of the way because they are repelling the others more. So finally, we will then state the shape that is formed and the bond angle. So 3 bonding pairs and 1 lone pair. We could actually draw it on like this. We'd have H. Oh no, that wouldn't be H. Let's try that again. Nitrogen, and we would have hydrogen, hydrogen, hydrogen. So 3 bonding pairs and 1 lone pair form a trigonal pyramidal shape. It's not bipyramidal because obviously we have this lone pair there. This has a bond angle of 107 degrees. So that is really important to remember. Okay, fab. So what I'm going to do is I'm going to pop that back up for now. We'll leave it there for today. Tomorrow we are going to go. I'll stop. It should still be recording. I think. More pause recording.